At the end of the 19th century, physics appeared to be a nearly complete and triumphant science. Many leading scientists believed that the fundamental laws of nature had already been discovered, and that future work would only refine measurements to a few more decimal places. Classical physics, built on the foundations laid by Isaac Newton, James Clerk Maxwell, and Ludwig Boltzmann, seemed powerful enough to explain motion, heat, electricity, magnetism, and light. Universities taught these laws with confidence. Textbooks presented the universe as orderly and predictable, and young physicists were often advised that there was little left to discover. Yet beneath this surface of certainty, deep cracks were forming. The confidence of classical physics rested on two main pillars. The first was Newtonian mechanics, which described how objects move under the influence of forces. From falling apples to the motion of planets, these laws worked with astonishing accuracy. The second pillar was classical electrodynamics and thermodynamics, especially Maxwell's equations, which unified electricity, magnetism, and light into a single elegant framework. Together, these theories painted a picture of nature as continuous, smooth, and deterministic. Energy could take any value, matter behaved like tiny billiard balls, and the future could, in principle, be predicted exactly if the present was known. However, as experimental techniques improved during the late 19th century, physicists began to probe nature more deeply. New instruments allowed them to measure radiation, heat, and atomic behavior with unprecedented precision. It was here that troubling discrepancies began to appear. Experiments were producing results that stubbornly refused to fit classical predictions. These were not minor errors that could be blamed on faulty equipment or careless measurement. They were systematic, repeatable, and deeply unsettling. One of the most serious problems involved the nature of thermal radiation. When objects are heated, they emit electromagnetic radiation. A hot iron glows red, then yellow, and eventually white as its temperature increases. Physicists studied an idealized object called a blackbody, which absorbs all incoming radiation and emits energy in a characteristic way that depends only on its temperature. By the late 19th century, experimentalists had measured blackbody radiation spectra with great accuracy. The results were clear and precise. The problem was that no existing theory could explain them correctly. Classical physics attempted to describe this radiation using well-established principles. According to classical ideas, the energy of electromagnetic waves inside a cavity should be distributed evenly among all possible frequencies. This approach, combined with statistical mechanics, led to a prediction that as the frequency increased, the emitted energy should grow without limit. This result implied that a hot object should emit an infinite amount of energy at high frequencies, especially in the ultraviolet range. This prediction was so obviously wrong that it became known as the ultraviolet catastrophe. The ultraviolet catastrophe was more than just an embarrassing theoretical mistake. It represented a fundamental failure of classical physics. Experiments clearly showed that the energy emitted by a blackbody rises to a peak at a certain frequency and then drops off sharply at higher frequencies. There was no catastrophe in reality. Nature behaved calmly and sensibly, while theory spiraled into absurdity. This mismatch signaled that something was deeply flawed in the classical understanding of energy and radiation. At the same time, other problems were emerging. The behavior of atoms could not be explained using classical mechanics. According to classical theory, electrons orbiting a nucleus should continuously lose energy by emitting radiation, causing atoms to collapse in a fraction of a second. Yet atoms were stable, matter existed, chemistry worked. The classical model predicted a universe that could not sustain itself. There were also puzzles related to the photoelectric effect, where light shining on a metal surface can eject electrons. Classical theory suggested that the energy of ejected electrons should depend on the intensity of light. Experiments showed instead that it depended on the light's frequency. Increasing intensity increased the number of electrons ejected, but not their energy. This was another clear contradiction between theory and observation. Despite these growing problems, many physicists were reluctant to abandon classical ideas. The success of 19th-century physics had been overwhelming, and the notion that its foundations might be incomplete was difficult to accept. Instead, researchers hoped that small adjustments or clever mathematical tricks would resolve the discrepancies. The prevailing attitude was that nature must ultimately obey classical laws, and any contradictions were temporary obstacles. This was the intellectual atmosphere in which Max Planck worked. He was a deeply conservative physicist in the best sense of the word. He believed strongly in the absolute validity of physical laws and was committed to the principles of thermodynamics. Planck did not seek to overturn classical physics. In fact, he was emotionally and intellectually attached to it. The crisis facing physics was not, for him, an opportunity for revolution, but a problem demanding resolution. The sense of crisis at the end of the 19th century was therefore subtle and complex. On the surface, physics appeared complete and elegant. Beneath that surface, experimental evidence was quietly undermining its core assumptions. The contradictions were accumulating, but their full significance was not yet understood. Many physicists sensed that something was wrong, but few imagined how radical the solution would be. This tension between confidence and uncertainty created a unique moment in scientific history. It was a time when the old framework still dominated education and research, yet new facts refused to conform. The tools of classical physics were being pushed beyond their limits, revealing boundaries that no one had previously noticed. The crisis was not loud or dramatic. It unfolded slowly, through equations that failed to match data and theories that produced impossible results. By the closing years of the 19th century, it was becoming clear that the problem was not a lack of mathematical skill or experimental accuracy. The problem lay deeper in the very assumptions about how nature works. Energy, long treated as a smooth and continuous quantity, might not behave that way at all scales. Matter, once thought to be solid and predictable, might follow unfamiliar rules at the atomic level. This realization did not arrive all at once. It emerged gradually, through frustration and careful analysis. Physicists were standing at the edge of a conceptual cliff, though few realized how close they were to stepping over it. The crisis of classical physics was the silent prelude to one of the greatest revolutions in science. It set the stage for a new way of thinking about reality, one that would challenge intuition, reshape technology, and redefine humanity's understanding of the universe. This was the world just before December 1900, a world where physics seemed complete yet was quietly failing, where certainty masked confusion, and where a solution to one stubborn problem would soon open the door to quantum theory. As the 19th century drew to a close, the growing crisis in physics was no longer confined to a single problem or laboratory. It was spreading across multiple areas of research, connecting phenomena that once seemed unrelated. What made this situation especially unsettling was that each new contradiction emerged from experiments of increasing precision. The more accurately physicists measured nature, the more clearly classical theory failed to describe it. This was not a temporary inconvenience. It was a warning that the old framework was reaching its limits. The faith in continuity was one of the deepest assumptions of classical physics. Energy, space, time, and motion were all thought to vary smoothly. There were no sudden jumps in nature, only gradual changes. This belief was so deeply ingrained that it shaped not only equations, but also intuition. Physicists expected nature to behave like the mathematics they used: continuous, elegant, and predictable. When experimental data contradicted this expectation, the instinctive response was to blame the experiment, not the theory. Yet experiment after experiment confirmed the same unsettling truth. The distribution of energy in radiation cavities refused to obey classical rules. Atomic spectra revealed sharp lines instead of smooth ranges of emitted light. These lines indicated that atoms emitted and absorbed energy at specific, well-defined values. Classical theory had no explanation for why nature would choose such precise patterns. The universe appeared to be selective, even economical, in ways that theory could not justify. This selectivity hinted at an underlying order that classical physics could not access. It suggested that the microscopic world operated according to principles fundamentally different from those governing everyday experience. Still, many physicists resisted this implication. The success of classical laws in describing macroscopic phenomena was undeniable. Bridges stood, machines worked, and planets followed predictable paths. It seemed unreasonable to abandon such a powerful framework because of strange behavior at scales too small to see. The crisis was also philosophical. Classical physics was deeply tied to determinism, the idea that the future is fully determined by the present. If all positions and velocities were known, the future could, in principle, be calculated exactly. This view aligned well with a mechanistic understanding of the universe, one that had dominated scientific thought since Newton. The emerging problems threatened this world view. If classical laws failed at the atomic level, then determinism itself might be incomplete. There was also an emotional dimension to the crisis. Many physicists had devoted their lives to mastering and extending classical theory. To admit that it might be fundamentally flawed was to question the value of decades of work. As a result, the scientific community moved cautiously. Radical ideas were viewed with suspicion, and conservative interpretations were preferred. The crisis unfolded slowly, not because evidence was lacking, but because acceptance was difficult. In laboratories across Europe, measurements continued to pile up. Spectroscopy revealed that each element had a unique fingerprint of spectral lines, implying a structured internal arrangement of atoms. Classical models could not account for this stability or specificity. According to existing theory, atoms should radiate energy continuously and collapse. Yet matter persisted. The everyday fact that objects retained their form became, paradoxically, a profound mystery. The inability of classical physics to explain stability was particularly disturbing. Stability is a basic requirement for any physical theory describing the real world. If the laws predict that matter cannot exist in a stable form, then those laws cannot be complete. This realization slowly eroded confidence in the classical picture. It suggested that the foundations themselves, not just the surface details, needed revision. The crisis also revealed the limits of analogy. Classical physics often relied on familiar mechanical pictures to explain unseen processes. Atoms were imagined as miniature solar systems, waves as ripples on a pond. These analogies worked well within certain boundaries, but failed dramatically at the atomic scale. the microscopic world refused to behave like a scaled-down version of the macroscopic one. New concepts would be required, even if they defied common sense. As the century ended, physics stood in a state of unresolved tension. The old theories still dominated classrooms and textbooks, yet they could no longer claim universal validity. Young physicists entering the field encountered a strange contradiction. They were taught a framework described as complete, while active research was uncovering problems that framework could not solve. This gap between education and research was itself a sign of crisis. What made this moment historically unique was that the crisis was not immediately visible to the broader public. There was no dramatic failure, no technological collapse. The crisis existed primarily in equations, graphs, and laboratory notebooks. It was a quiet breakdown, unfolding in the minds of scientists who struggled to reconcile theory with reality. This quiet nature made it all the more profound. The search for solutions became increasingly creative. Physicists experimented with hybrid approaches, combining classical ideas with empirical adjustments. Some proposed new constants, others modified existing laws. These efforts reflected a growing awareness that something fundamental was missing. However, without a guiding principle, progress was slow and uncertain. It was in this atmosphere of intellectual strain that Max Planck made his decisive move. Although he did not intend to trigger a revolution, his work was shaped by the pressure of this crisis. The failure of classical physics to explain blackbody radiation forced him to consider an assumption that contradicted everything he believed about continuity. The crisis narrowed the available options until only an unthinkable step remained. Looking back, it becomes clear that the crisis of classical physics was not a failure in the negative sense. It was a necessary stage in the evolution of scientific understanding. By exposing the limits of existing theories, it created the conditions for a deeper and more accurate description of nature. Without this crisis, there would have been no motivation to question the continuity of energy or the deterministic picture of the universe. The end of the 19th century thus represents a turning point. Physics did not collapse, but it did transform. The recognition that classical laws were incomplete opened the door to a new way of thinking. The crisis forced scientists to confront the possibility that reality is stranger than intuition suggests, governed by rules that only reveal themselves under careful scrutiny. This unresolved tension, this quiet but profound breakdown of certainty, set the stage for the birth of quantum theory. The crisis of classical physics was the shadow that preceded the dawn. It marked the moment when confidence gave way to curiosity, and when the limits of old ideas made space for something entirely new. At the end of the 19th century, one specific problem began to dominate discussions among physicists and quietly expose the weaknesses of classical theory. This problem centered on something seemingly simple and familiar: the way objects emit light and heat. When any object is heated, it glows. At low temperatures, it emits invisible infrared radiation. Then, as the temperature rises, it glows red, then yellow, and eventually white. This everyday observation had been known for centuries, but understanding it at a fundamental level proved far more difficult than anyone expected. To study this phenomenon precisely, physicists introduced the idea of a blackbody. A blackbody is an idealized object that absorbs all incoming radiation and reflects none. Because it absorbs perfectly, it also emits radiation in a way that depends only on its temperature, not on its material or shape. This made blackbodies ideal for theoretical and experimental study. By the late 19th century, Laboratories across Europe were producing extremely accurate measurements of blackbody radiation using heated cavities with small openings. The radiation escaping from these cavities behaved almost exactly like that of a perfect blackbody. What experiments revealed was strikingly consistent. For any given temperature, the emitted radiation followed a smooth curve when plotted against frequency or wavelength. The intensity increased with frequency, reached a clear peak, and then declined sharply at higher frequencies. As the temperature increased, the peak shifted toward higher frequencies, and the total emitted energy increased. These results were reliable, repeatable, and precise. Nature was clearly following a well-defined rule. The challenge was that no existing theory could fully explain this rule. Classical physics offered two partial explanations, each successful in a limited range but failing outside it. At low frequencies, the Rayleigh-Jeans law matched experimental data fairly well. It was derived using classical electromagnetism and statistical mechanics, assuming that energy was shared equally among all possible modes of vibration. At high frequencies, however, this law predicted something absurd: infinite energy output. According to the equation, the intensity of radiation increased without bound as frequency increased. This prediction had no basis in reality. On the other hand, Wien's law worked well at high frequencies but failed at low ones. It described the rapid drop-off of intensity at short wavelengths, but underestimated radiation at longer wavelengths. Physicists found themselves in an uncomfortable position. Two different formulas worked in two different regions, but neither could explain the full spectrum. There was no single theoretical framework that could account for all observations. This failure was deeply troubling because blackbody radiation should have been an ideal test case for classical physics. The system involved only electromagnetic waves and thermal energy, both of which were supposedly well understood. There were no complex chemical interactions or unknown forces involved. If classical physics could not explain something this fundamental, what else might it be missing? The deeper issue lay in the assumptions behind classical theory. According to classical ideas, electromagnetic radiation inside a cavity could exist at any frequency, and each frequency mode could carry any amount of energy. Statistical mechanics then assumed that energy would distribute itself evenly among all these modes. While this assumption worked well for many systems, it led directly to the ultraviolet catastrophe when applied to radiation. The ultraviolet catastrophe was not merely a mathematical curiosity. It was a conceptual disaster. It implied that a hot object would emit enormous amounts of energy at high frequencies, far more than was observed. If this were true, everyday objects would constantly release intense ultraviolet radiation, making life as we know it impossible. The fact that this did not happen meant that classical theory was fundamentally misrepresenting reality. Physicists attempted various fixes. Some suggested that matter might absorb high-frequency radiation more efficiently, suppressing the predicted explosion of energy. Others proposed modifying the equations of electromagnetism or introducing arbitrary cutoffs to limit high-frequency modes. These approaches were unsatisfactory. They lacked physical justification and seemed like mathematical patches rather than genuine explanations. The blackbody radiation problem became increasingly symbolic of a broader crisis. It demonstrated that classical physics, despite its success, could not be universally applied. The problem was not a lack of effort or intelligence. It was the structure of the theory itself. Classical physics assumed continuity everywhere. Energy flowed smoothly, frequencies formed an unbroken spectrum, and physical quantities could vary without restriction. The experimental evidence from Blackbody radiation suggested otherwise. What made the situation especially tense was the growing precision of experimental data. By the 1890s, measurements of Blackbody spectra were so accurate that theoretical curves could be compared in fine detail. The mismatch between theory and experiment was undeniable. There was no room left to argue that the discrepancy was due to experimental error. Nature was speaking clearly, and theory was failing to listen. The problem also challenged intuition. Light had long been understood as a wave phenomenon, especially after Maxwell's equations unified optics with electromagnetism. Waves were continuous by nature. The idea that light might behave in a discontinuous way seemed contradictory. Yet the Blackbody radiation problem hinted that something about energy exchange between matter and radiation was not continuous after all. This realization was uncomfortable and unsettling. It suggested that the classical picture of waves filling a cavity, each vibrating independently and sharing energy equally, might not reflect how nature truly works. The cavity, once imagined as a simple container of waves, became a battleground between theory and experiment. The Blackbody problem also had practical implications. Understanding thermal radiation was important for industries involving heating, lighting, and energy transfer. It mattered for astronomy, where the radiation from stars could be approximated as Blackbody emission. A correct theory was not just philosophically desirable, it was practically necessary. As physicists struggled with the problem, it became clear that incremental adjustments would not suffice. The failure occurred at the level of first principles. Any successful explanation would need to rethink how energy is emitted and absorbed at microscopic scales. Yet no one was prepared to take such a step openly. This intellectual tension created a unique atmosphere at the turn of the century. Physics was advancing rapidly, yet its foundations were under strain. The Blackbody radiation problem stood as the clearest sign of this strain. It was precise, well-defined, experimentally grounded, and theoretically devastating. In hindsight, the importance of the Blackbody problem lies not only in its solution, but in what it revealed about the limits of classical thinking. It forced physicists to confront the possibility that nature does not always conform to smooth, continuous laws. The failure of classical physics here was not due to negligence, but to the discovery of a deeper layer of reality. As the year 1900 approached, the Blackbody radiation problem remained unsolved. It loomed over theoretical physics like an unanswered question that could no longer be ignored. The stage was set for a radical idea, one that would emerge not from a desire for revolution, but from the necessity of matching theory with fact. This unresolved problem was the doorway through which quantum theory would soon enter physics. But at this stage, it was still simply a problem, persistent, precise, and profoundly unsettling. It showed that classical physics, for all its power, had reached a boundary it could not cross. At the center of the scientific upheaval that led to quantum theory stood an unexpected figure, Max Planck himself. Unlike many revolutionary thinkers, Planck was not driven by a desire to overturn existing ideas. He was, by temperament and training, a deeply conservative physicist who believed strongly in the validity and permanence of physical laws. His approach to science was careful, disciplined, and respectful of tradition. This makes his role in the birth of quantum theory all the more remarkable. Planck entered the Blackbody radiation problem with a clear intention. He wanted to find a mathematical expression that would fit the experimental data while remaining consistent with classical physics. At the time, precise measurements of Blackbody spectra were already available, and the failure of existing formulas was undeniable. Planck saw this as a technical challenge rather than a philosophical crisis. He believed that with enough effort, the correct equation could be derived from known principles. For years, Planck worked within the framework of thermodynamics and electromagnetism. He relied heavily on the concept of entropy, which he regarded as a fundamental and absolute law of nature. His goal was not to invent new physics, but to preserve the old by extending it just enough to explain the observations. This mindset shaped every step of his reasoning. As he analyzed the data, Planck became increasingly frustrated. The experimental curve of Blackbody radiation stubbornly refused to align with classical predictions. Neither the Rayleigh-Jeans law nor Wien's law could explain the full spectrum. Planck realized that simply adjusting equations would not solve the problem. The mismatch was too systematic, too precise, to be dismissed. Faced with this impasse, Planck took what he later described as an act of desperation. He made a mathematical assumption that went against his deepest beliefs about continuity in nature. He proposed that the energy exchanged between matter and radiation did not occur smoothly, but in discrete amounts. These small packets of energy were proportional to the frequency of the radiation, linked by a constant that would later bear his name. At the time, Planck did not interpret this assumption as a statement about physical reality. To him, it was a formal device, a way to make the equations work. He viewed quantization as a trick of calculation, not a fundamental feature of nature. In fact, he struggled to accept the implications of his own idea and hoped that a classical explanation might eventually replace it. Yet this assumption achieved something no classical approach could. It produced an equation that matched experimental data perfectly across all frequencies. The Blackbody radiation curve emerged naturally from the formula, without infinities or contradictions. For the first time, theory and experiment were in complete agreement. Planck presented his results in December 1900, unaware that he had initiated a revolution. His solution resolved a specific problem, but it also introduced a concept that would reshape physics. By suggesting that energy is quantized, even as a mathematical convenience, Planck opened the door to a new understanding of the microscopic world. The true significance of Planck's work became clear only in the years that followed. Other physicists, notably Albert Einstein, took the idea of energy quanta seriously and applied it to different phenomena. What Planck had treated as a reluctant assumption became the foundation of quantum theory. Planck's role in this transformation highlights an important truth about scientific progress. Revolutions do not always begin with bold declarations. Sometimes they arise from careful, conservative efforts to save existing theories. Planck did not seek to change physics forever, but by honestly confronting a problem and accepting an unthinkable assumption, he did exactly that. The introduction of energy quantization was not a confident leap into new territory, but a reluctant step taken under pressure. Max Planck did not arrive at this idea because it aligned with his intuition or philosophical beliefs. On the contrary, it directly challenged his understanding of nature. Yet the failure of every classical approach left him with no other option. Quantization emerged as an assumption born from necessity, not ambition. Classical physics treated energy as a continuous quantity. Whether in motion, heat, or radiation, energy was thought to flow smoothly, capable of taking any value. This assumption worked perfectly at everyday scales and had never been seriously questioned. Planck himself was deeply committed to this view. He believed that discontinuities in nature were artificial, signs of incomplete understanding rather than real features of the physical world. While analyzing Blackbody radiation, Planck attempted to model how energy was exchanged between matter and electromagnetic waves. He imagined oscillators in the walls of a heated cavity absorbing and emitting radiation. Classical theory allowed these oscillators to exchange energy in any amount. But when Planck used this assumption, he encountered the same contradictions that plagued earlier models. The equations either failed to match experimental data or led to infinite energy at high frequencies. Confronted with this failure, Planck made a radical move. He assumed that the oscillators could only exchange energy in discrete amounts, proportional to the frequency of the radiation. Instead of a continuous range, energy came in small steps. Each step was equal to a constant multiplied by the frequency. This constant, later called Planck's constant, set the scale of these energy packets. Planck did not believe that energy itself was fundamentally quantized. He saw this assumption as a mathematical convenience, a way to apply statistical methods more effectively. In his view, quantization was a feature of the calculation, not of nature. He later admitted that this step felt like a desperate act, taken only because all other routes had failed. Despite his reluctance, the results were extraordinary. With the quantization assumption in place, Planck derived a formula that perfectly matched the observed Blackbody radiation spectrum. The curve rose smoothly, reached a peak, and declined exactly as experiments showed. There was no ultraviolet catastrophe, no divergence at high frequencies. The problem that had resisted solution for years was resolved almost instantly. The success of this assumption forced a re-evaluation of its significance. Even if Planck did not initially accept quantization as physically real, the accuracy of the results could not be ignored. Nature behaved as if energy exchange were quantized. The assumption worked not approximately, but precisely. This moment marked a profound shift in physics. For the first time, continuity was broken at a fundamental level. Energy, long regarded as infinitely divisible, now appeared to have a smallest unit of exchange. This idea contradicted centuries of physical thought and challenged the wave-based understanding of radiation. What made the shift especially striking was its origin. Quantization did not arise from experimental observation alone, nor from philosophical speculation. It emerged from a mathematical struggle to reconcile theory with data. The equations demanded it, even when intuition resisted it. In this sense, quantization was imposed by nature itself. The reluctant nature of Planck's assumption underscores the depth of the crisis classical physics faced. When a conservative physicist is forced to introduce a concept that violates his own beliefs, it signals that the existing framework has reached its limit. Quantization was not an optional idea, it was the only remaining path. Although Planck hesitated to embrace the full implications of his work, others would soon recognize its revolutionary power. What began as a desperate assumption would become the cornerstone of quantum theory. Energy quantization transformed physics from a continuous, deterministic picture into one where discreteness and probability play a central role. This episode reveals an essential aspect of scientific discovery. Progress often begins with uncomfortable ideas, introduced reluctantly and accepted slowly. The assumption of quantized energy was not celebrated at first. It was tolerated because it worked. Yet from this hesitant beginning emerged a new understanding of the universe, one that continues to shape modern science and technology. December 1900 stands as a quiet but decisive moment in the history of science. There was no dramatic announcement, no immediate recognition that the foundations of physics had shifted. Yet in that month, a boundary was crossed that would forever change how humanity understands nature. The significance of this moment lies not in its outward appearance, but in what it set into motion. On December 14, 1900, Max Planck presented his results on Blackbody radiation to the German Physical Society in Berlin. His presentation was technical, focused on deriving a formula that matched experimental data. To those in attendance, it appeared to be a successful resolution of a specific problem in thermal radiation. There was little indication that this work would later be seen as the birth of quantum theory. What made this moment a turning point was the introduction of a new principle, even if it was not fully recognized at the time. By assuming that energy could be exchanged only in discrete units, Planck had broken with the classical idea of continuity. This single step, taken to solve a narrow problem, quietly undermined the assumptions that had guided physics for centuries. The importance of December 1900 becomes clearer when viewed in retrospect. Classical physics had reached a state of internal tension. Its laws worked remarkably well in many areas, but they failed in others with increasing precision. The Blackbody radiation problem was not an isolated anomaly. It was a symptom of a deeper issue. Planck's solution did more than fix a curve on a graph. It revealed that the classical framework was incomplete. At the time, few physicists grasped the full implications of Planck's work. Many regarded the quantization assumption as a mathematical trick, useful but physically insignificant. Even Planck himself hoped that a more traditional explanation might eventually replace it. Yet the fact that the formula worked so perfectly gave the idea a quiet authority. It could not be dismissed. December 1900 also marked a shift in how theory related to experiment. For much of the 19th century, theory had often led the way, predicting phenomena before they were observed. In this case, experiment forced theory to change. The data from Blackbody radiation experiments were too precise and consistent to ignore. Theory had to adapt, even if it meant abandoning deeply held beliefs. This moment signaled the beginning of a new era in physics, though it would take years for that era to fully emerge. Planck's constant, introduced almost incidentally, would later become a fundamental parameter of nature. It defined the scale at which quantum effects become significant and set a limit on how finely energy can be divided. Its presence in equations marked the boundary between classical and quantum descriptions. The turning point of December 1900 also reshaped scientific attitudes. It demonstrated that even the most successful theories have limits, and that progress sometimes requires accepting ideas that seem unnatural or counterintuitive. The willingness to follow evidence, even when it leads to uncomfortable conclusions, became a defining feature of 20th century physics. In the years that followed, other physicists would build upon Planck's work, revealing the depth of the change that had begun. Einstein would apply quantization to light itself, Bohr to atomic structure, and others to the foundations of mechanics. Each advance traced its roots back to that December presentation. What makes December 1900 truly remarkable is how understated it was. A revolution began not with a declaration of new physics, but with a careful attempt to preserve the old. This quiet turning point reminds us that history often changes direction not through dramatic gestures, but through small, necessary steps taken in moments of intellectual honesty. December 1900 thus represents the moment when physics stepped into the quantum age, even if it did so unknowingly. It marks the instant when the path of science bent away from classical certainty toward a deeper, stranger understanding of reality. The introduction of Planck's constant marked a profound shift in the way nature was understood. At first glance, it appeared to be just another numerical factor in an equation, added to make the mathematics work. Yet this small constant carried enormous meaning. It revealed a fundamental limit built into the fabric of the universe, a boundary that classical physics had never anticipated. Planck's constant emerged from the relationship between energy and frequency in Planck's radiation formula. It connected the size of the energy quanta to the frequency of radiation, acting as a bridge between the microscopic world of atoms and the macroscopic world of observable phenomena. The constant was extremely small, which explained why quantum effects were invisible in everyday life. Classical physics worked so well precisely because Planck's constant is tiny compared to the energies we normally encounter. Despite its small size, the constant carried revolutionary implications. It set a minimum scale for action in nature, meaning that certain physical quantities cannot be made arbitrarily small. This idea directly contradicted classical assumptions of infinite divisibility. Energy, momentum, and even information about a system were no longer continuous in the absolute sense. There was a graininess to reality that could not be smoothed away. At the time, Planck himself did not fully grasp the depth of this implication. He introduced the constant as part of a calculation, not as a declaration about the structure of the universe. Yet once it appeared, it refused to remain confined to a single problem. The same constant surfaced again and again as physicists explored new phenomena. Its repeated appearance signaled that it was not an artifact of a particular model, but a universal feature of nature. Planck's constant soon became a dividing line between classical and quantum physics. When systems involved actions much larger than the constant, classical laws provided accurate descriptions. When actions approached the scale of the constant, classical predictions failed, and quantum behavior emerged. This insight clarified why classical physics had worked so well for centuries while still being incomplete. It was not wrong, it was limited. The constant also reshaped the relationship between knowledge and measurement. In classical physics, it was assumed that measurements could, in principle, be made with unlimited precision. Planck's constant implied otherwise. It suggested that there are fundamental limits to how precisely certain pairs of physical properties can be known. This idea would later be formalized in the uncertainty principle, but its roots lay in the presence of this tiny constant. Beyond theory, Planck's constant became a cornerstone of technological progress. It governs the behavior of electrons in atoms and solids, making possible semiconductors, lasers, and modern electronics. Every transistor and digital device operates within constraints defined by this constant. What began as a solution to an abstract problem in thermal radiation became essential to the technologies that shape daily life. The philosophical impact of Planck's constant was equally profound. It challenged the classical belief in a fully deterministic universe. If nature is governed by discrete units and fundamental limits, then certainty must give way to probability at the most basic level. The universe is not a smoothly running machine, but a system governed by rules that allow only certain outcomes. What makes Planck's constant remarkable is how quietly it entered physics. There was no immediate recognition that it represented a new law of nature. Yet over time, its significance became undeniable. It unified diverse phenomena under a single principle and revealed a hidden structure beneath the surface of reality. In this sense, Planck's constant is more than a number. It is a symbol of the quantum revolution itself. It marks the point where classical intuition fails and a deeper understanding begins. By setting a fundamental scale, it defines the boundary of what can be known and predicted. The discovery of this constant reminds us that profound truths can be hidden in the smallest details. A number introduced to fix an equation became a window into the nature of reality. Through Planck's constant, physics learned that the universe is not infinitely divisible, but structured at its core. The reshaping of reality brought about by quantum theory was not an immediate or dramatic transformation, but a gradual and profound shift in how the universe was understood. What began as a technical solution to a narrow problem grew into a framework that challenged the most basic assumptions about nature. Quantum theory did not merely add new details to physics. It altered the meaning of concepts such as energy, matter, causality, and certainty. Before quantum theory, reality was viewed through the lens of classical determinism. The universe was imagined as a vast machine governed by precise laws. If the positions and velocities of all particles were known, the future could be calculated exactly. This view offered a comforting sense of order and predictability. Quantum theory disrupted this picture by revealing that at fundamental scales, nature does not behave in a fully predictable way. One of the most striking changes was the introduction of probability into the heart of physical law. Quantum theory showed that outcomes can only be predicted in terms of likelihoods, not certainties. Even with complete knowledge of a system's state, only the probabilities of different results can be known. This was not a limitation of measurement or technology, but a fundamental feature of reality itself. The nature of matter was also redefined. Classical physics treated particles as solid, well-defined objects with precise properties at all times. Quantum theory revealed that particles can behave like waves, spreading out in space and interfering with themselves. Their properties are not fixed until measured, and they can exist in multiple possible states simultaneously. This challenged everyday intuition and forced a reconsideration of what it means for something to exist. Energy, once thought to flow smoothly, was revealed to be exchanged in discrete amounts. This quantization explained atomic stability and the structure of matter. Atoms no longer appeared as miniature solar systems, but as quantum systems governed by allowed and forbidden states. Chemical behavior, the periodic table, and the nature of bonding all found their explanation within this new framework. Quantum theory also transformed the understanding of observation. In classical physics, measurement was seen as a passive act that revealed pre-existing properties. Quantum theory showed that measurement plays an active role. The act of observing influences the system being observed. This blurred the boundary between the observer and the observed, raising deep questions about objectivity and reality. The implications extended far beyond philosophy. Quantum theory became the foundation of modern technology. From transistors and lasers to medical imaging and quantum computing, its principles are embedded in the tools of contemporary life. Technologies that rely on precise control of matter and energy at small scales would be impossible without it. Perhaps most importantly, quantum theory reshaped the scientific mindset. It taught physicists to accept that nature may not conform to classical intuition. The success of quantum theory demonstrated that accuracy and predictive power matter more than comfort or familiarity. Reality does not have to make sense in everyday terms to be true. This shift also highlighted the evolving nature of scientific knowledge. Quantum theory did not render classical physics obsolete. It placed it within a broader context. classical laws remain valid where quantum effects are negligible. This layered understanding showed that scientific theories are approximations, each with its domain of applicability. The reshaping of reality brought by quantum theory continues today. New interpretations and extensions are still being explored, and its implications for information, computation, and the nature of space and time are actively studied. What began in December 1900 has become an ongoing journey. In transforming how reality is understood, quantum theory stands as one of the greatest intellectual achievements in human history. It revealed a universe that is subtle, probabilistic, and deeply interconnected. By challenging certainty and redefining fundamental concepts, it permanently changed not only physics, but humanity's view of its place in the cosmos.